Knots. If you fly a lot, you've heard the captain say it 1,000 times, usually like a throwaway line. Cruising at 500 knots. Winds at 20 knots. Ever connect that word to a knot, like the kind you tie in a rope? Because your brain immediately goes, no way, what does rope have to do with a jet at 35,000 feet? I mean, come on, rope? But here's the funny part, yeah, rope. If I told you, we're literally flying at rope speed, I'm not joking. That's basically what this unit comes from. Wait, what? How did a term sailors used at sea become the official speed unit for jets? And with GPS, satellites, and sensors everywhere, why are we still using a unit born from rope and an hourglass? Welcome to Simple but Surprising. Today, we're untangling the story of the knot. To understand why rope speed became official, you've got to rewind to the 1600s. No GPS, no radar, no little screen politely telling you recalculating, just ocean in every direction and a crew that really, really wanted to know one thing. How fast are we moving? Because speed at sea isn't trivia. If you don't know your speed, you can't estimate distance. And if you can't estimate distance, you don't know where you are, which is a fancy way of saying you can get lost or you can meet a reef up close. Neither one is fun. So sailors came up with this brilliantly simple gadget called a chip log, and it's exactly as low-tech as it sounds. Picture a small piece of wood-shaped, kind of like a slice of pizza. They'd weight it so when it hit the water, it would stand up and resist being dragged along. That little wooden pizza was tied to a long rope wound on a reel. And this rope wasn't random. It had actual knots tied into it at perfectly measured intervals. Here's how the whole speed test went down. When it was time to measure, the officer would call for it. One sailor tosses the wooden chip over the back of the ship. The chip stays more or less in place because water is heavy and stubborn. Meanwhile, the ship keeps moving forward, pulling the rope off the reel. At the same moment, another sailor flips a small sandglass, an hourglass calibrated to run for 28 seconds. Now the job is simple. The sailor holding the rope lets it slide through his fingers and counts the knots as they whip past. 1, 2, 3, and when the sand runs out, someone yells, "Stop!" and they grab the line. If 5 knots passed in that timed window, the ship's speed was 5 knots. That's not a metaphor, that's literally where the unit comes from, counting rope knots moving through your hands. After the count, they'd tug the line so the chip flipped flat, created less drag, and was easy to pull back in. So yeah, knots was originally just knots in a rope. Count how many go by, and you've got speed. But here's the part that makes this way smarter than it sounds. Those knots weren't spaced because vibes. They were spaced so the number you counted matched something way bigger than the ship. Because the real measuring stick out there wasn't a road. It was the earth, and that's where it gets really interesting. So why did they bother tying those knots at such a weird, picky distance? Because out on the ocean, sailors weren't really navigating by roads, they were navigating by a grid. Latitude, longitude, the Earth's built-in coordinate system. On land, we're spoiled. You can measure distance with mile markers or signs, or just places that exist. At sea, everything looks like the same blue screen shot for days. So sailors leaned hard on the planet itself, 360 degrees around, and each degree split into 60 minutes. And they set a simple rule: 1 nautical mile would equal the distance of 1 minute of latitude. So on a chart, if you nudge your position by exactly 1 minute of latitude, that's 1 nautical mile traveled. If 1 nautical mile is your map distance, then the perfect speed unit is simply nautical miles per hour. And that's a knot. 1 knot equals 1 nautical mile per hour. So back to the chip log rope. The goal wasn't just count knots. The goal was count knots and instantly know nautical miles per hour. Right there on deck, no calculator, no debate. That's why the spacing looks random. Somebody did the math so that if you let rope run for a standard 28 seconds, the number of knots that passed would match your speed in nautical miles per hour. A nautical mile is a little over 6,000 feet. Divide that by 3,600 seconds in an hour, then multiply by 28 seconds, and you land right around 47 feet and a few inches. So they tied knots about 47 feet 3 inches apart, flipped the 28-second sandglass, counted what passed, and wrote down the speed. It's basically an analog speedometer made from rope, but it's also tied directly to the geometry of the Earth. And once you see that, knots stops sounding like an antique word sailors refuse to let go of. It's a speed unit that plugs straight into navigation on a round planet. Which brings up the next obvious question. If knots are Earth geometry speed, that actually explains ships. So why are airplanes still speaking the same language up in the sky? Okay, so for ships, knots make perfect sense. You're moving across the surface of the Earth, you're navigating with latitude and longitude, and nautical miles per hour fits right into that system. But airplanes? A modern jet is basically a flying computer with wings. It can tell you the outside temperature, the wind, your ground speed, your airspeed, probably your personality type. So why is it still using a unit that started with rope and an hourglass? Because planes don't actually escape the map, they just move across it faster. Early, long-distance flying was heavily tied to oceans, coastlines, and navigation methods sailors already trusted. Pilots weren't just pointing the nose and hoping for the best. They were navigating on the same Earth grid, degrees, minutes, and long stretches where landmarks don't exist. And even today, aviation is built around that same global language. Routes are planned over the curved surface of the planet. Positions are given in latitude and longitude. Distances are often handled in nautical miles, so keeping speed in knots makes the math match the map. And there's another key detail. Pilots care about airspeed, not just how fast you're moving over the ground. Because the atmosphere is moving too. A jet can be doing the same airspeed on 2 different days, but one day there's a tailwind and you're flying faster over the ground, and the next day there's a headwind and you're crawling. Knots work cleanly for that world because it plugs into the same navigation system used for headings, routes, and position reporting. It's not old-fashioned as much as it is compatible. So when a pilot says, "We're cruising at 500 knots, it's not a cute tradition. It's the modern version of the same idea sailors used. Speed that connects directly to navigation on a round Earth. Which means that one weird word, knots, ties together a wooden ship, a rope with knots in it, and a jet flying at 35,000 feet. Different century, same planet. And next time you hear knots, you'll know you're not just hearing a number. You're hearing a piece of Earth geometry, with a little bit of rope still hanging off it. Thanks for watching Simple But Surprising. If you enjoyed this one, hit like, subscribe, and drop a comment. Have you ever actually stopped to think about where knots came from? Or did you just accept it like everyone else? See you in the next one.